Who's my ancestors? They're not. They're French Canadian. The history is it used to be R-A-D-I-O-U-S. But then they changed it as huge. No, but they kept the revenue pronunciation. It's very, but yes, it's revenue.
Yeah, she's working with now. Yeah, yeah, isn't that so funny? Roommates with like everybody in our room. Yeah,
I know. I like so the last time I did this talk on this topic, so I pulled up myself. She worked on just we're on a lot of this technical stuff, but I
so it's so funny. Like most of our roommates talk like statistics based. We're like, hey,
throughout, but I'll try to see how it makes sense. So I figured I'd try to tailor it for both statisticians.
Yeah, I know it's great.
Fortunately, I think these methods are pretty flexible. This stuff are actually taken.
Yeah, we should have started like
getting a model.
Yeah.
I actually think it's a very, it would be a nice method as a sense.
Yeah, no, it's great.
Okay. Love to actually use this. And now I'm here because I was I think they close one another. Because I saw it this afternoon. Yeah. That's awesome. Okay. I realized that why it's most of the classes watch. It's really exciting. They record everything. And now after the pandemic, recording. Really discouraging. It was like I'm here. It was also an 8 a.m. class. Like
Okay. Is this functioning?
It is functional.
Okay.
Then you go as far as probably it's like here and here moving the slides. That's
Okay. Thank you.
And then I'll pop up and switch over slides.
Okay. I'm barely taller than the podium.
it's okay. The camera's going to show up there.
Okay. Good. Okay. Okay. Good afternoon, everyone. Thank you for coming on this Thanksgiving week. I'm Katie Colborn. I am the director of the Biostatistics and Analytics Core at Accords. And I want to welcome you all to today's Accords Education Seminar program. So just a little bit about Accords first. We're supported by the University of Colorado School of Medicine and Children's Hospital, Colorado. We're a unique one-stop shop environment for faculty to conduct pragmatic research, receive various types of services and support for grants and projects, along with incredible mentorship, training, and education in health services research. Specifically, we conduct pragmatic research in real-world settings to improve healthcare and outcomes. We have a multidisciplinary collaborative research environment, strong methodological cores and programs, and we do consultations and team building for grant proposals. We offer mentorship and training to support faculty, early stage investigators, and extensive educational offerings like this one that we have today. And these are offered both locally and nationally. Okay, next slide. So before I introduce our speaker today and hand over the floor to him, just a couple of housekeeping items. Please first use the chat throughout the seminar to share questions and comments. And we will have time for moderated question and answer at the end of the talk. And second, please complete the evaluation at the end of today's seminar so we can continue to provide the best seminars and educational offerings for our local and national audiences. Are you going to be monitoring the chat? Okay, thank you. So today I'm very excited to announce our seminar speaker as a part of our Statistical Methods for Pragmatic Research. This is the third of 9 talks in this series, and we are very excited to welcome Dr. Dustin Rabideau today. Dr. Rabideau is Associate Director for Biostatistics and Strategic Initiatives for Massachusetts General Hospital Biostatistics. He's a faculty biostatistician with MGH and an assistant professor of medicine at Harvard Medical School. He serves as co-investigator and senior biostatistician on local, national, and international research projects in psychiatry, cancer, and infectious diseases. And Dr. Rabideau also leads 2 active areas of biostatistical research: robust analysis methods for cluster randomized trials and innovative methods to account for participant dropout in clinical trials. And I'll just say that I'm lucky to work with him on a project, a multi-site trial of acute myeloid leukemia patients. So please join me in welcoming Dr. Dustin Rabideau today as he presents randomization-based inference for cluster randomized trials.
I'm glad to be here, and I'm glad so many of you could make it in person and on Zoom shortly before the Thanksgiving holiday. Really appreciate the dedication. Awesome. Thank you so much. All right, so as Katie said, I'm a faculty biostatistician at Massachusetts General Hospital. I'm very glad to talk to you about some work that's near and dear to my heart that actually came out of my dissertation research. So it's actually stuff I haven't thought about for a couple of years. So it was a very nice excuse to get back to this and hope to kind of teach you about randomization-based inference, something I knew very little about before my dissertation and know something more about now, just to give you another tool in your statistical toolkit that you can use. All right, so most of you are probably familiar with individually randomized trials, where we randomly assign people to some intervention or treatment. So here I've depicted kind of randomly assigning people to 2 groups. One is kind of a red shot and the other is a black shot. So these are kind of typical individually randomized trials. So what's different about a cluster randomized trial or a CRT? So a cluster randomized trial is just a randomized trial in which groups or clusters of people are randomly assigned to interventions. So here I've depicted down below, instead of each person receiving a randomly assigned intervention, we have these groups of people assigned to a particular intervention. So the example cluster randomized trial I'll talk about today is this one called the Botswana Combination Prevention Project. So this is a large HIV prevention cluster randomized trial where 30 communities in Botswana were randomly assigned to 2 different HIV prevention intervention strategies. One was a combination prevention package, and the other was a standard care package. So 15 communities were randomly assigned to receive combination prevention, and another 15 were assigned to receive standard care. In cluster randomized trials, even though the intervention itself is assigned to these communities, oftentimes the outcome that they measure is on an individual level. So in this study, the primary outcome was HIV infection measured at an individual level at annual study visits. So just quickly, some reasons why you might consider conducting a cluster randomized trial. These are kind of 3 of the most common reasons for going about randomization in a cluster group way. The first is oftentimes there are interventions that are just more naturally or more feasibly applied at a cluster level. So for example, this combination prevention package, it was very easy to roll this out at a community level. This is how it would be implemented in practice. And so that's why they went about randomizing clusters rather than randomizing individuals. They can also avoid treatment contamination. So if we had individually randomized some people in one community to receive this combination prevention package and others to receive standard of care, it might be that because this is an infectious disease setting where one person's disease status might impact another because of the way infectious disease spread, that could actually introduce contamination between the 2 treatment groups. So one person's intervention could actually impact another person's outcome. So because they've rolled this out at a cluster level and everybody in a given community received one intervention, you kind of avoid this treatment contamination issue. The third major reason is they capture these population level or indirect effects of the intervention. So again, in the Botswana study, not only can you measure kind of these direct effect of a treatment on a given individual and their outcome, but you really measure these indirect effects. So people within the community who might not have directly received the intervention may still benefit from a combination prevention package being rolled out among their community. So those are some of the benefits of a cluster randomized trial, but because we roll out this intervention at a cluster level, it introduces some statistical challenges. So I've listed 3 of these statistical challenges here. So because we are randomizing clusters or groups of people and measuring individual level outcomes, we introduce correlation between the outcomes within a cluster. So if I live in one community, my outcome may be more correlated to a person within my community than it is correlated with a person outside of my community. So we need methods that can account for this correlation. We're also often dealing with a small sample setting. Because our randomization unit is these groups of people, we typically have a smaller number of kind of independent randomized units. And so we can't rely always on statistical methods that rely on asymptotics or rely on a large enough sample for these approximations to be valid. In the Botswana study, we only had 30 clusters or 15 per group. Because we're dealing often with a small number of clusters, we might introduce features in our study design to control for balance, such as pair-matched randomization that was done in the Botswana study, to make sure that our 2 groups look similar. And again, in the analysis, we'd like to acknowledge this design feature. And there are ways of doing this, but it just introduces yet another statistical challenge we might be faced with in a cluster randomized trial. All right, so when you are going to analyze data from a cluster randomized trial, and you're dealing with individual level outcomes, there are kind of 2 typical regression approaches that you may take. You might go ahead and fit a mixed effects model, introducing random effects to account for this clustering. Or you might go down the marginal model or generalized estimating equations approach, using a different method for analyzing it that acknowledges correlation. Unfortunately, when certain distributional assumptions are not met, so if you make the wrong assumption about how correlation exists within a cluster, or you're dealing with a very small number of clusters, these kind of common regression approaches can lead to inaccurate p-values and inaccurate confidence intervals. In other words, they can lead you to the wrong conclusions being drawn from your cluster randomized trial. So what I'm going to talk to you about today is an alternative approach you could consider taking called randomization-based inference. Randomization-based inference goes by many names. You may have heard kind of permutation methods for the statisticians in the room, or re-randomization tests. And there's been a recent resurgence of interest in randomization-based inference, specifically for cluster randomized trials, because of some attractive features that this approach provides you. And those advantages are, first, that it is distribution-free. So we do not require certain distributional assumptions to be made about our outcome, and it also does not require you to make particular assumptions about what structure of correlation within your clusters exists. The other advantage is that these methods are exact in the sense that their validity does not rely on you having a large enough number of clusters. So I'm going to explain to you how you can calculate randomization-based p-values and confidence intervals today. But some of the challenges of these methods are that they're less common, which I hope to mitigate some of that today for at least the people in the room by explaining to you and introducing you these methods. But they may be kind of less familiar if you go to use them in your study and then you write your paper and the reviewers might not be familiar. So one of the challenges is just that they are not as common as linear mixed effects models or the usual kind of correlated data regression approaches. Second, there's more computational time required, and you should get a sense of why that is once we talk about how you actually conduct randomization-based inference. And then a lot of this work has focused on randomization testing and calculating p-values, and less work has been done on corresponding confidence interval methods. So obviously there's been a push in the recent several years of the statistical community to focus more on not only on p-values and testing, but also on estimates, confidence intervals, that kind of thing. So this is another kind of limitation where I focused a lot of my work on coming up with a way we could calculate randomization-based confidence intervals. All right, so this is randomization-based inference, and our goals for today, let me just skip this slide. So our goals for today are, first, I'm going to describe to you how you can actually conduct a randomization test. So what steps you would take if you were going to go about conducting a randomization test and getting a p-value. Then we're going to learn how you can calculate randomization-based confidence intervals. And then we're going to apply these methods to reanalyze the Botswana combination prevention project. And just before we get to the actual nitty-gritty of calculating randomization-based p-values and confidence intervals, I just wanted to give you yet another piece of motivation that led to this work focused on randomization-based confidence intervals. So it turns out in this Botswana combination prevention project, which we'll reanalyze later together. So this was a big study published in the New England Journal. And the authors actually pre-specified using a permutation test or a randomization test for their primary outcome. But they didn't have a corresponding way of calculating a confidence interval. So what they actually did is they conducted a randomization test. They got a p-value of 0.09, which they had pre-specified kind of 0.05, the common threshold for statistical significance, which they failed to meet here. But they didn't have kind of a corresponding way of calculating a confidence interval. So they needed to rely on a different method of calculating their confidence interval, and actually got a confidence interval that excluded that null value of 1. So they kind of published this paper and have, obviously this 0.05 is not a magic number, but it is unappealing to kind of present your results in a way where your p-value kind of fails to reject your null hypothesis, but your confidence interval doesn't correspondingly include that null value of 1. So anyways, my work was really motivated by coming up with a way we could actually calculate a corresponding randomization-based confidence interval for this study. Okay, so I'm going to try to, focus this talk on gaining intuition behind randomization-based inference, but I am going to have some notation and a couple Greek symbols spread throughout for our statistical folks in the audience. But I really hope that what you'll take away from this is the bigger picture intuition for the idea of conducting randomization-based inference. Okay. But the setting I'm going to be focusing on today is a parallel cluster randomized trial with 2 treatment groups. The number of individuals per cluster could vary. That's not something we're kind of controlling to be equal. So these clusters, these communities in the Botswana study had members involved anywhere from 100 people in the incidence cohort to 300. So the cluster size can vary. I'm going to use Y to denote our outcome of interest. In the Botswana study, this was kind of HIV infection. And then we're going to use X to denote our intervention group. So X is going to be this binary or dichotomous variable where 1 is for people in the intervention group and 0 is for people in the control group or the standard of care group. Subscripts here you can ignore if you don't like symbols, but YKI is the outcome for the ith individual in the kth cluster. So you can see that X is just denoted with a K subscript because, again, we're in a cluster randomized setting. So everybody in the kth cluster has either intervention or control. All right. So before we get into conducting a randomization test, I'm going to define what we are interested in estimating or testing, or how we're going to quantify our treatment effect of the intervention X on the outcome Y. So I've written down in mathematical notation here this treatment effect theta that is a difference in mean outcome between the intervention clusters and the standard of care clusters. So if you just imagine you have a continuous outcome Y and you ignore the G's for a minute, theta just represents a difference in mean outcome between treated clusters and control clusters. If we're dealing with a binary outcome Y and the logit link function here, theta just represents the log odds ratio between intervention clusters and control clusters. So kind of these common quantities we're familiar with in public health and biomedical research. And we're interested first in kind of conducting a randomization test of no treatment effect. In other words, a difference in means of 0, or a log odds ratio of 0, or an odds ratio of 1. So the actual process of conducting a randomization test and coming up with a p-value can be broken down into what I think are 3 very simple steps. So first, we're going to take our observed data set. So we end this cluster randomized trial. We've measured a bunch of outcomes on people. We know which intervention group they were assigned to. We're going to take that data set and we're going to fit a regression model with that observed data set and get some coefficient estimate of this estimated treatment effect. So maybe that's just a linear regression model with a binary term for treatment. We're just going to fit that model, get our estimated treatment effect, and that's our first step done. The second step just involves shuffling treatment assignments, refitting a model, and getting an updated coefficient. And we're going to do that a bunch of times. So step 2 is going to be repeated over and over again, where we are just shuffling treatment assignments within across the clusters, refitting our regression model, and getting a new coefficient. Then we're going to take this collection of coefficients that we've calculated, and we're going to calculate the proportion of estimates that are as or more extreme than the original observed treatment effect estimate. So again, we're going to go through each of these steps in a little bit more detail, but the essence of what we're doing involves fitting our regression model with observed data, shuffling things and refitting a regression model, and then calculating a proportion. Things that I think everybody in this room could probably do if we broke it down into those elements. Okay. So the first step, let's talk a little bit more about this. So the first step, we are going to fit a model with our observed treatment assignments. And here I'm denoting those treatment assignments with a bold X. But in essence, we're just taking our observed data set and we're going to fit a very simple regression model. Here, I'm considering a generalized linear model where we're relating kind of our mean outcome to a really simple linear form on the right, where we have an intercept term and we have a term for our treatment effect, X. I've included, for those of you who are familiar with R, I've included just some R code. If you don't know R, you can just tell by the length of this code how simple fitting a model like this would be. But essentially, we are just going to fit a linear model or a generalized linear model with Y as our outcome, X, which is our binary 0-1 treatment, in our data set, and we're going to extract the coefficient related to treatment. And I just want to note something here, that we are fitting a model, a GLM, that is typically used in the independent data setting. So we're not explicitly acknowledging correlation in our regression model like we would with a random effects model or with GEE. We are just fitting a very simple regression model to extract a coefficient estimate. All right, so now we've fit that model on our observed data. We've gotten one estimated treatment effect. Now what we're going to do is we're going to shuffle or permute our treatment assignments, refit that same model, but now instead of using the original zeros and ones that we observed for our randomized trial, for our cluster randomized trial, we're going to use this permuted column of ones and zeros. All right, so let's talk about how we're going to do this in a little more detail. So let's go down to this picture down here for a minute. So let's say we've run this cluster randomized trial that involved 6 clusters, for example. And in reality, when we randomly assigned clusters, we happened to randomize clusters 1, 2, and 3 to the intervention group, denoted by x equals 1 here. And we randomly assigned clusters 4, 5, 6 to the standard of care group. So this first row in this table just represents the observed treatments, the observed treatment vector that actually occurred in our trial. So when we go to shuffle treatment assignments, all we're going to do is randomly shuffle these ones and zeros across the clusters in our data set. So if our data set involves individual level outcomes, we're going to be permuting entire chunks of ones and zeros because those ones correspond to everybody in that given cluster. But in essence, we're just re-randomizing, re-shuffling these ones and zeros across the clusters and using that new column in our data set of ones and zeros to calculate a new regression coefficient. And then we're going to just reshuffle again, recalculate, reshuffle again, recalculate. And we're recalculating that using the same regression model we had used before, but rather than using our observed treatment column, we're going to use our kind of permuted column. One other important aspect of this is that the way we shuffle these ones and zeros depends on the actual design of the study. So if we designed the study using, in the sense that we randomly assigned 3 clusters to intervention, 3 clusters to control, we didn't include any kind of stratification or restricted randomization, we would just permute in an unrestricted fashion. But if, in fact, we designed the study using some restricted randomization scheme, we could actually incorporate that into the way we permute the data here, which we'll get into a little more detail in a later slide. But I just wanted to say that. But in essence, all we're doing is shuffling ones and zeros in our data set and refitting our regression model. Okay, so now that we've done this a bunch of times, we have our observed theta hat, our observed treatment effect estimate, and then we have a bunch of other treatment effect estimates based on those permuted data sets. Now we're going to take this list of theta hats, and we're just going to calculate the proportion of them that are as or more extreme than the one based on the observed data. So here I've just drawn a picture of, let's say we did 500 permutations of our data. We have 500 different theta hats, and we're going to plot the distribution of those theta hats, and we're going to see how extreme was the one we observed in our study compared to the rest of these permuted treatment effect estimates. And we're going to quantify that extremeness by saying how many were kind of beyond that in terms of their absolute value. If here we're considering a 2-sided test. So I've highlighted kind of the density of this distribution that lies as or more extreme than the one we observed. And it turns out that it's about 6% of our distribution. And so our randomization-based p-value would just be 0.06. All right, so that's how we would conduct a randomization test and calculate a randomization p-value. So then what the bulk of my dissertation work actually focused on was how can we use this idea of permuting or re-randomizing treatment assignments and calculate a corresponding confidence interval using the same approach. And it turns out, like in theory, this is a known thing that I didn't come up with, but with permutation or randomization-based inference, what you need to do is kind of what's called invert this randomization test to calculate a corresponding randomization-based confidence interval. So what do I mean by invert this randomization test? What I mean is you need to conduct many different randomization tests to see which thetas are reasonable. So far, we talked about conducting this randomization test for no treatment effect. So we were interested in conducting a test for a specific null value, theta equals 0. Now we're just going to have to figure out how we can do this for other values other than 0. And then we're going to, once we figure out how to do that, we're going to do it a bunch of times across a bunch of different values. And that's going to be the basis for forming this randomization-based confidence interval. Okay, so again, I've broken down, and we'll get into more detail. I've broken down how to calculate a randomization-based confidence interval into 3 steps. The first step is the bulk of the complexity, which is conduct a randomization test now for a non-zero null value. So maybe we're interested in testing a null value of theta equals 1 or theta equals 2. So how can we do that using this framework we've set up? Step 2 is going to be repeat step 1. So once we understand step 1, we can just repeat it. And we're going to be changing that null value, theta 0, and conducting a new test, and then conducting a new test. And then in the third step, we're just going to collect all of the theta 0s that were not rejected by a randomization test. And the bounds of this set form our confidence interval. Okay, so again, we're going to break down each step. This is the dentist slide, so we're going to move through this a little slowly. So first, how do we conduct a randomization test for a non-zero null value? So it turns out we can kind of add and subtract terms, like is often done in statistics, and show that we can actually reformulate this problem of conducting a randomization test for a non-zero null value by introducing an extra term in our model that then allows us to reformulate the problem into one of testing a zero null hypothesis. And so what do we need to introduce into our model? It turns out we just need to introduce this additional term, theta 0 x, that is formally called an offset term. So you may have heard of offsets in regression models, like when you're dealing with Poisson regression, you often add like an offset for log follow-up time. It's just a term in your regression model that takes a fixed value. So it's not something you're interested in estimating, it's just some fixed value that you're inserting into your regression model. And what you can do, it turns out, is once you've introduced this offset into your regression model, it leaves this offset adjusted treatment effect term. And you can reformulate the problem of conducting a randomization test of a non-zero theta value to one of calculating a randomization test for a zero null hypothesis, but on this offset adjusted term. So what we are going to do is we're going to consider, so for a given theta 0, let's say we're interested in conducting a randomization test of the null hypothesis of theta equals 1. We're going to introduce this offset term where this number here would just take the value of 1. And then we're going to conduct that same randomization test we talked about in the last section on this offset adjusted treatment effect term, tau. The important piece to know when conducting this randomization test is we're going to do slightly different things for this fixed offset than we're going to do for this offset adjusted treatment effect term. And what that boils down to is we're going to use, so we're going to permute treatment assignments just as we did in the last section on this offset adjusted term, but we're going to fix them at their observed value across permutations for this offset adjusted value. So these x's are always going to be the same, and we're only going to kind of incorporate those permuted treatment assignments into this treatment effect, offset adjusted treatment effect term. Okay, so even if I've lost you here, I just want to bring it back to what it actually involves, which is it just boils down to conducting a randomization test the same way we did before by taking those 3 steps of fitting a model on the observed data, permuting a bunch of times, calculating a p-value. We're doing that same thing, but now we have just introduced a single additional term into our model. And again, you can see here that it's just a matter of introducing a fixed offset term into your regression model. and then conducting that whole randomization test procedure for a given value, theta 0. Okay, so hopefully I've convinced you that this is possible for a given theta 0. Now step 2 is we just need to repeat this procedure across a bunch of different theta 0s. So we're gonna pick, we're gonna kind of explore the possible parameter space of thetas and see which ones we would fail to reject a null hypothesis and which ones we would reject a null hypothesis using this randomization test. And then we're just gonna collect the group of them that we did not reject, and that's gonna define our confidence set. And the extreme kind of entries in that set are gonna define our randomization-based confidence interval. So here I've just kind of depicted in a picture, like what we did on the first randomization test slide is test this 0 null hypothesis, and we ended up getting a p-value of 0.06. Then we're gonna define this new non-zero null, let's say theta equals 0.5. We're gonna introduce that fixed offset into our model, we're gonna conduct that randomization test, and we're gonna get a different p-value. And then we're gonna move that theta 0 up to 1, let's say, reconduct that randomization test, calculate a p-value, do that. And we're gonna do this across many, many different theta 0s, and then collect the group of them that resulted in a kind of non-significant p-value. And the bounds of that grouping are gonna form our 95% confidence interval if we're testing at a 0.05 level. So here in this picture, our resulting 95% confidence interval would be -1.5 to +0.5, because those are the tests for which we failed to reject the null hypothesis. The other ones we kind of rejected at a 0.05 level, so those are kind of excluded from our confidence interval. Okay, the last thing I want to say about this actual approach is that you can kind of get the sense that when we're doing a randomization test consisting of hundreds, maybe thousands of permutations of data, and then we're doing this across many, many different potential theta 0 values, this is something that can kind of really grow in terms of its computational complexity. So you can imagine that fitting a GLM might take a second, but then each randomization test is going to take 500 seconds. And then if we're looking across hundreds of different theta 0 values, it just expands even further. So typically, this is something that might take hours to days to actually compute a single confidence interval, depending on the data set size. Another piece of our work was adapting this efficient search algorithm that essentially removes one of the dimensions of complexity and makes it possible to calculate these randomization-based confidence intervals in a more reasonable amount of time. So something that takes seconds to minutes. I'm not going to go into the details of this algorithm, but we'll see kind of a picture and can talk more about it if you're interested in it. Okay, so before moving back to the Botswana combination prevention project and starting to apply some of these methods, I want to point out two more things. The first is something I mentioned earlier, which is randomization-based inference has this really nifty way of accounting for study design features. So let's say because we're dealing with usually a small number of clusters, we might have stratified randomization on important variables we thought we wanted to kind of control for balance across the randomization groups. When we get to the analysis, it's often ideal if we can kind of account for that. It turns out that if you account for that by including additional regression terms, you can actually gain some efficiency from that design feature. Take advantage of this balance that you controlled for in the design. And the typical solution, if you were going to go down kind of the common cluster data approaches, is to include additional terms in your model. So let's say you've stratified randomization on well, site is a bad example in a cluster randomized trial, but let's say there's some important clinical feature of the sites that you want to account for. Give me an example in scope. What did you stratify on? Do you know?
Racial
Okay. Okay, so yeah, so if you've stratified randomization on kind of the racial makeup or the demographic makeup of a site, you may include that in your regression model towards the end of the study to kind of, again, control for that source of variability. Unfortunately, this can, in some settings, it can change the value or interpretation of the parameter you're targeting by now targeting kind of an adjusted treatment effect, adjusted on race, or it can kind of exacerbate some, so it can lead to some instability. So as you know, you introduce more terms into your model, things can just start to get unstable. So randomization-based inference has a really nice solution that doesn't change your target of inference. It does not lead to more instability, but it's just natural in terms of its the way you implement it in the analysis. Like I mentioned, you would just, rather than kind of, when you're permuting these treatment assignments, rather than permuting in an unrestricted fashion, you just permute treatment assignments according to the way you permuted them in the design. So if you set up a randomization that was stratified on racial makeup, you would just acknowledge that when you get to the permutation approach, and you would only permute things in accordance with how that was done. In the Botswana study, for example, they used pair-matched randomization. So they matched communities based on a bunch of different characteristics, and then into pairs, and then for one of those within the pair, they got intervention, the other one, they got standard treatment. So when you got to the randomization-based p-value and confidence interval procedure, you would just permute things the same way. You would ensure that that pair was kept together and that one of them always got standard of care or treatment, but you would kind of randomly assign them within those pairs. So again, it's a really nice kind of design-based analytic tool that you can use to acknowledge and incorporate design features into your analysis. Okay, the last thing I'm going to say is that a lot of my work got spent creating an R package that makes all of this very easy to implement in practice. So you don't actually have to know how to permute things. You don't have to know how to calculate confidence intervals using this search algorithm. It's all involved in the background in my package that I would encourage you to try using and reach out if you have questions. It's on GitHub, so it's not on CRAN. So if you've ever installed something, for those who use R, if you've ever installed something that just lives on GitHub, this is how you do it. And then I just included some snippets of code, like all you have to do is kind of fit your regression model. And then there's these worker functions, perm test and perm CI, that you just give that regression model to. You define some other arguments to tell it where your certain data features exist, and then it does all of this for you. And there's actually very good documentation. I spent a lot of time, mostly for my own sanity and keeping track of things, that are in that package. So I just wanted to mention that too. All right, so we're now going to return to the Botswana Combination Prevention Project and use these methods to reanalyze this data set and just demonstrate to you some of the ways we can improve the analysis here. So just as a reminder, they had kind of this misalignment between their primary p-value and their primary confidence interval, where the p-value was based on randomization and the confidence interval was based on a different approach. It just so happened in this setting that they conflicted in terms of the kind of classic statistical significance concept. And so what we're going to do is we're going to first replicate this randomization test using this procedure that I've described to you. And then we're going to recalculate a confidence interval, now using this new randomization-based confidence interval approach using offsets in our models. All right, so a reminder, it turns out that the primary outcome in the Botswana project was HIV infection, and it was measured at annual study visits. So we actually had a somewhat more complicated outcome than usual. So it's this interval censored time to event outcome. And I've just given you just a snapshot of what, this is fake data, but this is kind of what the basic data set looked like. So when you're in an interval censored, so what is an interval censored outcome? It's not actually super important for this, this method, but it essentially means that if people came in at their first year visit, they were not infected with HIV, they came in for their second year visit, they were infected at that time. We know that their infection date occurred sometime between year 1 and year 2, but we don't know exactly when. So that's what we mean by this interval censored time to event outcome, is we don't know precisely where that time to event lives, we just know where it happened in between. So again, this is just a snapshot of the data set where we have our kind of participant ID, we have 30 different communities and some identifier for each community. Again, I mentioned that this was a pair matched study. So the first two communities, 1 and 2, were defined this first pair where one of them received intervention and one of them received the standard standard care. Here's just our binary individual level outcome, HIV infection, and these left and right just define this interval censoring time. So for those without HIV infection during follow-up, it's just kind of your usual censored outcome where you have kind of your follow-up time. And what we do is we just assign the right censoring time as infinite because we know they did not have the event up until, I think these are days 754, but their right time is kind of infinite after that. For people that had the event, we have a window in which that event occurred, but we don't know exactly within this window when it happened. Okay. So if we were going to go first calculate a randomization test and calculate a randomization-based p-value, how could we do this using the R package and the techniques that we've talked about? So the first thing we need to do is we need to figure out what regression model should we use to estimate some treatment effect. And it turns out what we've done here is we've just used a parametric survival model, a Weibull model, that can accommodate this interval censoring. And it essentially spits out for us like a hazard ratio or a log hazard ratio. So in R, I've just fit this regression model, and then I use this perm test function, which conducts this randomization test. And what do I need to give it? So once we have our data set loaded, I fit the regression model and I feed into it that entire regression model object. And then I just need to tell R where certain variables live. So the first is R needs to know like which of your variables corresponds to the random treatment so that we can know which one to permute. And I've told it it's this column in our data set called TRT. Then I need to tell it what was our randomization unit, because it needs to know when permuting to keep all those random assignments together. Because like I mentioned, when we're in the individual data setting, if all the observations from our first community, for example, all received intervention, so when we permute, we're going to permute that entire intervention chunk we're going to permute in a way that acknowledges that everyone in community 1 should have either received intervention or standard of care. So we just tell R, that's our randomization unit. And then we can incorporate these design features using this strat argument. So here I've just told R, randomization was stratified by this pair match design. And so when you permute, you should acknowledge that design feature. And then we tell it like how many permutations we want to do. There's a lot more detail on how to choose that, but I've just chosen 5,000 permutations of our data here. Okay, so we run that line of code and it does this whole permutation test procedure by fitting and refitting. And then we can use some basic functions to like plot that permutation test like we looked at before. And it shows us where our observed estimate was, the distribution of our other permuted estimates, and it spits out a randomization-based p-value, which here we've replicated that 0.09 that was actually done in the original paper. And our estimate based on our observed data for the hazard ratio was 0.69, kind of favoring the combination prevention strategy. And just for a sense of how long this took, so on my laptop, 5,000 permutations, a pretty large data set, 8,500 observations, took about 2 minutes to calculate this p-value. Something within reason. Okay, so then when we go to calculate a confidence interval, again, we kind of understood the basic steps that need to be taken. This function perm_ci does all the work for you. And again, you just feed into it that original model fit from the servreg, and then you just tell it those same kind of variables of interest, the name of the treatment column, the randomization unit, and any design features, and then how many permutations of the data you want to use for this confidence interval procedure. And then it does all of that for you, this kind of randomization test, different null values, it does all of that internally. And it uses that kind of efficient search algorithm to search for those confidence limits. And that's what's depicted in this picture here. So this is the actual procedure. So it has some starting values, let's say based on the naive original regression fit. And then it starts permuting data and changing that null value up and down. And after a while, it starts to converge. And you pick off those final values of the search algorithm, and that defines your randomization-based confidence interval. So here, when we actually implemented this in this data set, we ultimately landed on this randomization-based confidence interval ranging from 0.37 to 1.04. And this, again, on this relatively large data set, a good number of permutations, took about 40 minutes to run on my laptop. So yes, it's not like instantaneous answer, but in the grand scheme of a 5-year trial, tens of millions of dollars invested, I think it's a reasonable amount of time to wait for a different alternative analysis with some robust characteristics. Okay. So again, just bringing things back. So we've now been able to calculate a corresponding randomization-based confidence interval and one that's actually in alignment with the p-value that was originally calculated in this Botswana study. All right, so I'm going to end here. I just want to summarize what we've talked about and then answer some questions. So just as a summary, randomization-based inference is a robust alternative analysis strategy that's especially useful for cluster randomized trials. And it's especially useful because, first, it does not make any assumption about distribution. So we don't have to define what distribution our outcome came from, and we don't have to make assumptions about the correlation structure within a cluster. And then it's also exact in the sense that it provides valid p-values and confidence intervals, even when we have a really small number of clusters. Conducting a randomization test just consists of fitting a regression model, shuffling treatment assignments, calculating a proportion that are as or more extreme, and then the confidence interval, we have to conduct multiple randomization tests over various non-null values, and then collect all of those not rejected by a test to form a confidence interval. So this was a really high level overview of these methods, but if you're interested in more, so the first paper is kind of focuses on this randomization-based confidence intervals for cluster randomized trials, a lot of what I talked about today for parallel CRTs with 2 treatment groups. We then extended this work to the step wedge trial setting where clusters are randomly assigned to cross over at certain times to from control to treatment, and how you can adapt these randomization-based inference methods to that setting. The third paper is not my paper, obviously, but a paper I found towards the end of my dissertation work, which clarified a million of these concepts, which I was really struggling with. And it gives a really concrete and straightforward overview of permutation methods and randomization-based methods. And I would recommend starting there for if you've never kind of worked with randomization-based inference or permutation methods and want a really quick, short paper about it. And then I would encourage anyone to give my R package a try. I put a lot of effort into putting this together, and I'd love to kind of involve more people in that and try to make it work for them. So thank you everyone for joining today in person and virtually. I'll leave it at that.
Thank you, Dustin. That was great.
We have a question in the audience.
Yeah, Dr. Ying.
Thank you. Very nice talk. I really appreciate. So I have a question. For you to do the confidence interval, right? You want to try different theta. So it's kind of like a grade.
Yeah.
Is that a building automatically choose the width of the grade?
Yeah. So let me go back to this. Right. So the way I described this was in its most basic sense, you could carry out this grid search, or this, I kind of demonstrated a grid search where you kind of pick a grid of theta zeros and you do that test at one theta zero, you do that test at another theta zero. What I've incorporated into the R package itself is actually not a grid search. It's this efficient search algorithm that what it does is, rather than conducting an entire randomization test at a single theta zero and then moving to another theta zero and conducting an entire randomization test, is what it does is it starts with some theta zero and then it permutes the data one time. It recalculates how does that coefficient compare to the last coefficient, and then it steps a theta zero up or down. So it's kind of similar to a binary search in a way, but it's kind of this adaptive search algorithm that kind of it kind of permutes the data once, calculates fits a model, calculates the coefficient, and then it steps that theta zero up and down, up or down, depending on some criteria. And then it permutes the data once again and steps up or down, depending on that criteria. So it's not a grid or a binary search, but it's kind of doing this iteration between permuting once, retesting, stepping up or down, permuting once, retesting, stepping up or down. And it turns out that this search algorithm, in theory, averages out to kind of get you to the confidence interval estimates you would have obtained had you done an entire grid search on every possible data value. So it's just this efficient, clever way of kind of getting that done without having to go through a grid search.
The other one is really small. I'm just curious. I see when you do the example, your p-value, you only use 5,000 permutation. And confidence interval, you have 20,000.
Yeah.
Any reason for that?
Yeah, so actually I go into a lot more detail in the paper about like there's a lot of fine tuning you can do with this. So you can typically you can base the permutations for your test on the Monte Carlo error of that test procedure. So you can, typically 5,000 is adequate in terms of like a p-value, which is essentially a proportion. So you would expect that to be pretty tight within the Monte Carlo error. But typically the search algorithm, you need more steps to get to something that's felt like it's converged. But yeah, there's a lot of fine tuning you can do in the R package. And in the paper, I actually talked through a lot of these like little things. How do you pick the number of permutations you do for the test or for the confidence interval? How do you can like choose the step size? How do you kind of choose starting values? You can actually use like multiple chains, almost like a Bayesian thing, but like, pick 4 different starting values and let this thing go. And you can monitor kind of how they converge or stabilize over time to kind of convince you that you've made it far enough in terms of the permutation. So yeah, there's a lot more in the paper about that, about how to choose these things.
Thank you. That's very exciting work. I already have your GitHub pulled up, so
awesome. Find all the bugs for me, please.
I'll do my best. I did have one question about the small sample problem in GE algorithms. Some authors have traced that back to really a problem that centers on the robust variance estimate.
Yep.
And several have proposed some adjustments to the asymptotic solution. Did you happen to compare to any of those?
Yes, actually I did. So I can just give you a snapshot. It's a lot more in the paper again, but there's a million simulation settings, but we examined one of these common small sample adjusted GEs in our simulations. I think it's depicted by, so there's this, I think it's Fay and Grabar paper. They came up with like 5 different ones. I think there's a package in R called SAMS. I don't know. They came up with 5 and then recommended this 5th one. So we kind of compared how our randomization-based confidence interval procedure compared to this small sample adjusted GEE, and found mostly that like with a very small number of clusters, these small sample adjustments can kind of overcorrect in a sense. So they can lead to kind of confidence interval coverage that's higher than your nominal target, whereas the unadjusted GE does really poorly in the other direction. As you get more and more clusters, they kind of all equal out the methods, but you can gain a bit of efficiency and maintain your nominal coverage, at least compared to this one small sample adjusted GE. So there's a lot of work. There's a great paper, I can send it around after, that talks about like cluster randomized trials with a small number of clusters, like what analytic strategies you can use. They compare a lot more of these small sample adjustments for GEs and for mixed models. The challenge is like, certain adjustments can perform well in one setting and not well in the other. And it's hard to know exactly that. The beauty of randomization-based inference is that you're guaranteed to have nominal coverage in all settings. So that's one advantage. But yeah, we compared it to one of these small sample adjusted GEs. Are there questions? Yeah.
I have a really simple question. My question is, would the sample size for each cluster affect your permutation results?
The cluster size should not impact validity of a permutation test or permutation confidence interval. But I could imagine it has an impact on efficiency, like precision of that estimate, just as it would impact kind of, but yeah, I know there's like an interplay between the number of clusters and the cluster size, especially when it comes to kind of asymptotic methods. My intuition off the top of my head is that it should not impact permutation methods. Like all of this could be applied to an individual level data, like an individually randomized setting, where you can imagine that each person is their own cluster. It can be applied to kind of settings where you have a small number of clusters, but a huge amount of people. That's kind of what this setting was. It should not impact the validity. So you can still get type 1 error control and confidence intervals with nominal coverage, regardless of the within cluster sample size.
Thank you.
Yeah.
Okay, we have a few questions online. One is, what if you have covariates that you need to adjust for?
Great question. So this can be adapted to that setting. So you would then consider a covariate adjusted model. Rather than fitting a simple model that we did here, you could kind of incorporate covariates into your regression model and use the same process. Like you would just have a covariate adjusted treatment effect then. So here, rather than in this first step of the randomization test, rather than fitting a model with just treatment, you could introduce a covariate into your model. That obviously changes your target of inference and maybe the interpretation, but you can go through the same procedure of doing this, and every time you permute, you refit your model, but refit it with covariate as an additional term in your regression model. So yeah, it's a really flexible approach. You can adapt it to different regression model types, like we did a survival model. You can include covariates in your model. You could even consider doing it for mixed models. Things might get more complicated then in terms of like stability, but the actual process of conducting a randomization test, introducing an offset into your term is pretty general for common regression models.
One more question, if we have time. This individual asked about how do you communicate the concept and importance of this randomization-based inference to community members? What strategies did you use to ensure the understanding and buy-in of those communities? I don't know if you're involved with that part of the study.
I was not involved. Yeah, so that's a really good question. I don't know. I know they had so I wasn't involved. So the Botswana Combination Prevention Project, my advisor was involved in the study. Obviously, it got published before this method existed, or else they would have used this to calculate their confidence interval. I know they had a lot of community buy-in and partnership and stakeholders involved in the paper, the design, the study itself. I'd be very curious to know how they kind of, if they involved them in kind of describing this randomization test as the primary approach. I have no idea, but I'd be interested in hearing about that. But yeah, I think it's, because it's not as common, it's challenging in that it's hard to convince, any stakeholders in research, like reviewers or grant funders, to maybe think about this. These authors were clearly successful in using a randomization test for their primary outcome, but it's more challenging. But yeah. All right, well, thanks again, everyone. And obviously, if there are any questions, I'm always open on email. Feel free to shoot me an email, especially if you start to use my R package and have questions. But yeah, thanks everyone for coming and joining remotely. I know you're up there on the camera.